Okay, so we're going to work out a few of these related rates problems for you. This first one, I believe, is number 10. This is what we call a shadow problem. Pretty common problem also, just like the conical tank problem. You've got a man here. He's walking. There's a light post here. Typically, shadow problems happen one of two ways. The man's walking away from a light, or the man's walking away. The light's on a post, or the light's on the ground and the shadow's on the wall. That's number 12. So you got this man walking away from the light, and they're asking you how fast the tip of his shadow is moving when he is like 10 feet away from the wall. Okay, so the first thing that this is the light here. It's kind of janky. Okay. The first thing we're going to do is look at the picture in the book. The picture in the book, I believe, is slightly misleading because they labeled this 10. Okay, and I don't know that you want to label things in your picture that are changing. I don't know that you want to label them with a constant, because if they're changing, they're typically going to be labeled with a variable. Okay, so I'm going to call this distance right here y, and that distance x. Okay, so the distance between the tip of his shadow and him, and the distance that he is away from the wall. You could flip-flop those, it doesn't matter. Okay, now it tells me I know that dx dt equals 3, okay? Because the man is walking away from the wall at a rate of 3 feet per second or whatever. So this distance right here is changing at a rate of 3, okay? I want to know how fast this point is moving, okay? Well, this point is actually represented by that distance right there, which I'm going to call L. I don't know why I used L, maybe for length. I'm not sure why I used L. But I want dl dt, and when do I want it? I want it when y equals 10, when he's 10 feet away from the wall. Okay? So there's what I know, there's what I want. I've assigned some variables. I got a nice picture. So now I need to essentially find a relationship between x and L and y, okay? So if I look at this, I see two similar triangles. I see L over 10, this side over this side, equals x over 6, okay? So there's my similar triangles. So there's my equation that relates some of these variables. So I'm going to differentiate this equation with respect to t, and I'm going to get 1/10 times dl dt equals 1/6 times dx dt. Okay? So dl dt then is going to be 10/6 times whatever dx dt is. So I solved, and now I'm going to substitute. So I'll plug in what I know. Dx dt is a constant 3. And I get 30 over 6, or 15 halves, whatever, feet per second, or whatever. Okay? It's interesting in this problem that this answer was not dependent on what y was. Okay? When this rate right here was 3, that answer, how fast this length is changing, did not depend on what y was. Okay? And in fact, it doesn't really even depend on, it depends on that rate, but it didn't necessarily depend that it was 3. If this would have been 7, we would have just had a 7 there. Okay? So, again, be careful with the book, because the book sometimes will label things that are constant that aren't constant, so we don't want to be careful about that. And then, once you got your picture set up, your nose, your once, and there's your equation. Okay? Number 12 is a little different, which I'll erase the board and do right now. Okay, so here's number 12. I've drawn part of the picture. Again, oh wait, the book actually didn't draw a picture for this one, so I'll go through my process of drawing the picture with you. So I've got the light on the ground this time, shining towards the man, and now there's a wall, and his shadow's going to be on the wall. So this is different than the last problem where the shadow was on the ground. And the man's walking towards the wall away from the light, right? So I'm going to call this distance right here x, the distance that he is away from the light. And then I'm going to call this distance right here y. Okay? And I think it's pretty clear then that if this whole thing is 40, because that's the light's distance from the wall, then this distance right here would be 40 minus x. Okay? So there's the things that are set up. Okay, I'm not plugging in I'm not setting any numbers in here. I'm relabeling the things that are changing. All right, and then I'm going to say, well, what do I know? What do they tell me? I know he's walking towards the wall at a rate of 2. So I know dx dt equals 2. Okay, I want to check my picture because I want to make sure I labeled this right. So give me 1 second. Okay, so we're back. I had just said I wasn't 100% sure I set my picture up when I did it. I worked this out yesterday afternoon, and I think I was confusing 10 and 12 in my head, so I wanted to make sure I had everything set up the way I wanted it. So back in this problem here, and so we know that dx dt is changing at a rate of 2. So he's walking towards, he's walking that way towards the light, right? No, he's walking towards the wall. Sorry. He's walking towards the wall at a rate of 2. So dx dt is 2. Ooh, I need some more coffee. Dx dt is 2, okay? And then what are they asking for? They're asking for his shadow's on the wall, right? And they're asking for, like, this, if you think about it, that length right there is his shadow, which I'm going to call y. They're asking for what's dy dt when he's 30 feet from the wall. So we have to do some thinking here. If he's 30 feet from the wall, that means that this distance right here, when he's 10 feet from the wall, that means that this distance right here has to be 10, which means this distance right here has to be 30. So it's going to be dy dt when x equals 30. Okay? So let me just say that again because I know that can be confusing. They want to know how fast is this length changing when he is 10 feet from the wall. So if he's 10 feet from the wall, which is that distance right there, that means that 40 minus x has to equal 10, which means that x has to equal 30. Okay? So now we've got a picture set up. We know we want to write some equation that relates these variables, x and y. Okay, this is an x here. Looks kind of goofy. So what's our equation? So let's look for some similar triangles. So how about y over 40 equals 5 over x? Okay, now I'm going to be crafty here. I'm going to be sneaky because if I differentiate this right now, I've got x to the negative 1 power, and maybe that's just ugly. You can still do it this way, but I'm going to actually rewrite this equation as x times y equals 200. And now I'm going to differentiate this with respect to t. Okay? And so just like Mrs. Austin, my high school calculus teacher, would have said, you got to use the product rule here. So it'll be the derivative of the first. So that'll be dx dt times the second, y, plus the derivative of the second, dy dt times the first, x. And what's the derivative of 200? 0. So dy dt times x is equal to negative dx dt times y. And then if I divide, dy dt equals negative dx dt, times y divided by x. Okay, so I've solved, now I'm going to substitute. So all of these things on the right side I know. Either they were constants or they're the value of when I want to take the picture and freeze everything. So dy dt is going to equal negative dx dt, which was 2, times y. So I don't know what's y, right? What is y when x is 30? What's y when x is 30? Okay, well, I've got to go back right here and say, well, what's y when x is 30? X times y equals 200. So 30y equals 200. So y is 200 over 30. So I'm going to put that here, 200 over 30. And then we do some math, or I should say some arithmetic, which you could do on a calculator if you want. You end up getting, I believe, -4/9 is your answer. Okay? So now, let's talk about what does that negative mean? Okay, what does this negative mean? Well, that means that dy dt is -4/9. That means that this distance right here, as he gets closer to the wall, the length of the shadow is shrinking. Okay? So that's why the back of the book says the shadow is shrinking at a rate of 4/9, whatever, meters, feet per second, or whatever it is. So this is the other type of shadow problem. By the way, right here, you could have just as easily differentiated this and got, right here, I'll do it. You could have gotten 1/40 times dy dt equals, and just thought of this as 5x to the -1 equals -5 x to the -2 times dx dt. And you could have done it that way, and you would have gotten the same answer. So, okay, so next problem is coming up. Okay, so problem 35 here, problem 35. This is saying, this is similar to the conical tank problem, but it's a conical pile. It says gravables being unloaded from a truck, falls into a pile shaped like a cone, at a rate of 10 feet cubed per minute. The radius of the cone base is 3 times the height of the cone. Okay, so that basically is saying they're giving you the relationship between R and H. Unlike the conical tank problem, which we had to figure out the relationship between R and H using similar triangles, here they're just giving us the relationship between R and H. It's saying that the radius is always 3 times the height. Okay, so my picture is not really accurate, but that's okay. I'm just going to write here R equals 3H. Okay, so yeah, I want to make sure you could see that. I'm still not happy with that. It looks crappy, so let's fix that. R equals 3H. Okay? And so what do we know in this problem? What are they telling us? They're telling us that the volume of the cone that's happening there, that dV dt is equal to 10. Okay? And then what do we want to know? We want to know, it says, I think, how fast is the height of the pile changing? So that's going to be, what's dH dt when, I think, h equals 5. Okay? So there we go. We've got our nose. We won't have our once. We've got a nice picture. So let's set it up. So we find an equation relating V and H. Well, we know that the volume of a cone is 1/3 pi r squared h. Okay? That's got 2 variables in it, right? We don't know anything about dr dt necessarily. So we could just take this value for r equals 3h and just plug it in. Like that. So now we've got the equation for the volume all in terms of h. Okay? Incidentally, I said we don't know anything about dr dt. We do know how dr dt and dh dt are related. I challenge you maybe to think, like, look at this equation right here and kind of tell me, how is dr dt related to dh dt? That's a separate problem that I might challenge you to think about. It's not too terribly difficult to do using this idea right here. But anyway, back over here. So I'm going to go ahead and clean this a little bit before I do any calculus. So I'm going to 1/3 pi times 9 squared, or 3 squared is 9, h squared times h, so that's going to be times 9h cubed. which then looks like 9 over 3 is 3. So that's 3 pi h cubed. Okay? So now I'm going to differentiate this with respect to t. So I have dv dt equals 27. Wait, 3 times 3 is 9, not 27. Nine pi h squared times dh dt. Okay? And now I'm just going to plug in the things that I know. So I know the dv dt, and this time I'm going to substitute then solve. So dv dt is 10 times 9 pi. I want to know this when h was 5. And then dh dt is the thing I'm solving for. Okay? One thing that kids typically do wrong when they're doing these related rates problems is they plug in this value of h too early. Okay? A lot of times they'll plug in this value of h before they took the derivative of it. Okay? You have to wait until you take the derivative of it and then plug it out. It's all about, we want to know how fast dh dt is, we want to know how fast h is changing, or we want to know dh dt when h is 5. So we have to differentiate first and then plug in the 5. Okay? It's like finding the derivative at a point, kind of. So dh dt here is going to be 10 over 9 pi times 5 squared. Okay? So that ends up simplifying, I think, to 2 over 45 pi. So there you go. 2 over 45 pi. And what are the units of that, by the way? It's going to be feet per minute, or I didn't label the units of, I think this was feet per minute. Okay? So that's problem 35. We'll clean off this board, and then we'll set up 36. Okay, so here's problem 36. Problem 36 is just an extension of 35. They just change it up. It's the same pile, same cone. They're just changing up. They're just giving you different rates out of the gate. And I think they're switching which rate they're giving you and asking you to solve for the other one. So in 36, now they're telling you that we know the height of the pile is changing at a rate of 4. So we know dh dt equals 4. And we want dv dt. When do we want it? I think it's actually at the same instant, when h equals 5. Okay? So we're still going to use the same relationship between r and h that we had before. So the volume function that we have here, that's volume all in terms of h, doesn't change. So we're going to just rewrite this, do it exactly like we did before. So that's 3 times 3 is 9, over 3 is 3 pi h cubed. And now we'll just differentiate this with respect to t. So dv dt is going to be 9 pi h squared times dh dt. And now we're just solving, we're plugging in 4 here and solving for dv. In fact, it's already solved for dv dt. So honestly, 36 is probably an easier problem than 35 because you don't have to do any algebra to solve for the thing that you want. So you just would plug in 5 here, plug in 4 there, and just do the arithmetic. So that's 4 problems on related rates. Keep working on these. You might want to look at maybe a problem next to one of the ones I assigned, see if it's similar, and see if you can do it, and then check the answer in the back. If you have any questions, don't hesitate to reach out as you're working on this. Peace.